Hello everyone, we are Team 6. Our project topic is post-wildfire air quality prediction in California. Our purpose is using wildfire features such as fire size, location, duration, and weather features such as temperatures and precipitation as inputs to predict air qualities through machine learning models. For this project, we only focus on wildfire happened in California, and the time frame we choose is between 2000 and 2015. We have three data sets as input. They are wildfire, weather, and air quality. Here is our today's agenda. First, we're gonna start with machine learning model and evaluation result. Then we will talk about comparative machine learning model results and finalize with web-based system design and implementation.
Okay, so as we discussed last time, so our machine learning model, so we have three. Because we have three air quality metrics, we have CO, ozone, and PM 2.5. So for each of the air quality metrics, we will find the best performing machine learning result. Since all of the quality metrics, they are in the decimal points or they are in the floating point number. So our best performing models, they will be all deep learning models. So as we see over here, so the first one we choose is the artificial neural network, which is our ANN model. And then as we know, we plot the we plot the loss curve versus the epochs. And as we can see from the graph, all of the graphs are trending downward. That means that our machine learning model is working as expected and is proving the effective of the deep learning model. And our second one is our revolutionary neural network model, recurrent neural network model. So as we can see, this one is not the this one over here on the left hand side for the ozone, it was quite smooth. It was quite flat for a whole period of time, which means for the RNN model is not performing as well as the ANN model. As we know, the ANN model has a gradually decreasing curve as well. This one is only gonna saturate after a few runs of the epochs. And the next one, we will have the GRU model, which is an improved version of the LSTM model. The reason we include that is because, as we know, the fire information as well as the weather is time sensitive. So by using the update gate and reset gate, we are able to record and take those factors into consideration so that our model is trying to be more accurate. And then, okay, go ahead, Michelle. And then afterward, we will plot and we will see which model performs the best for each of the metric.
Okay, we have tried three different machine learning models on the data set we got, but we have to choose the one that has best performance among those three. This slide and the following two slides show that the AN model outperformed the other two models in terms of loss, no matter which air quality index was put into the model. In addition, we also took the time efficiency into consideration, and the ANN model had the lowest runtime when compared with the other two models. Therefore, we decided to choose the ANN model as our ultimate model to predict air quality values and use the ANN model as the underlying model when we build our website for the demonstration purpose.
Okay, now let's go over to our website. Okay, Joe, go ahead.
Okay, so what are you looking at is our homepage for the website we have designed. And this website is fully functional and include everything we've done in this project, including visualizations, data sources, and air prediction simulation using our machine learning models. There are 7 tabs on the top, and we'll go into detail about each of them later. If you want to scroll down at the bottom, we gather some stats to just show you guys how much damage the wildfire have done to our environment as well as the economy. If you want to scroll down further, there are 4 machine learning models we have tested, and we ended up using ANN for our final model prediction in this project because it has the best accuracy among others. If you want to click on data preparation, here are all the raw data we have collected with all the detail info, including all the important columns we gathered and generated. They are all clickable, and if you want to click one of them, you will see the source where they're downloaded. So you can see this one is downloaded from Kaggle, which is our Wi-Fi data. So yeah, if you want to scroll down a little bit, this is just show our data cleaning and preparation process. The step 1 is to clean fire data and perform feature selections. And then we serialize weather data into Python object, which is dictionary that we used. Then step 3 would be we transform the data into machine learning model ready state. So yeah.
Okay. And then afterward we have our 2D and our 3D, and so we have our 2D and 3D plot. So basically our 2D plot from our exploratory data analytic result is that our 2D plot will plot the red interval over here represents where the fire starts, and then those are not highlighted indicate those without the fire start and end. So as we can see, those highlighted red portion indicating one of the air quality metrics. So for example, this one is represented for the CO, and it has so as we can see, CO is impacted by the fire dramatically. And then for the other one is doing the same thing for the ozone and PM 2.5. And then those are all for the major fire that occurs in the history, so that we will see the most significant change. And for our 3D plots, just so that the user understand what we are doing over here, is that so our 3D plot, it has 3 axes. Our target axis, which is our z-axis, is the target air quality matrix. We want to see what is the impact of that. And then our horizontal axis indicates each day during the year. So as we know, fire usually occurs in the autumn or the summer season. So we can see from this useful 3D graph the seasonality of the fire. And then our y-axis is also very important, which indicates the fire size. As we can see, during the so around 150 days to 200 days around the summer to autumn time, there was one major fire, which means our exploratory data analytic part is doing correctly, because as we can imagine, in California, most of those feel very significant fire occurs in the autumn season. And then if we navigate to the next part, so just for the collaboration purpose, if other developers or other data scientists want to see our project and how do we do this whole project, and our website raw source data, they can see all of those from here. So all of those tabs are clickable, and each one represents one of the important significant steps during our data cleaning and data processing step. And next one, we have the explore impact, which means this one is a tabular-based visualization. Okay, go ahead, Joe.
Sure. This visualization is done by Tableau, as David said. The purpose is to visualize all the wildfires happen through a timeline, so that we will have a better idea the location and season that wildfire happens often. So in this particular project, the data is gathered and prepared based on geographic information. Tableau provides an extremely easy to implement environment to represent data as a map format. After some dragging onto data dimension and acquire data measures such as fire size, air pollution, stats, and geo information. We have designed the visualization as a format of a Tableau dashboard containing two maps as filters for each other. There's also a draggable page legend that serves the purpose of picking a specific time range and move forward along the timeline automatically to represent the date as tooltip on map points. So the one on the left points out every Wi-Fi at the exact location given longitude and latitude. The one on the right gives Wi-Fi that happens during the time by county. So when you click on the county, so tooltip will give the exact numbers for the summation of fire size, CO, ozone, PM 2.5 concentration, and temperature at given range. So this sums up our visualization done by Tableau.
Yeah, so for this part is the first interactive web portal we have built, and this part is only involving the past data, past fire data, and user can customize their fire data, like they can select the county for happening the wildfire, and also they can decide their own fire size, and also they can decide the duration of the fire, and also they can define the mean precipitation and the mean max temperature, and those so whenever they define their own data for the fire, when they click on the predict, and it will come out the prediction value, which contains the CO value, ozone value, and PM 2.5 value. And also we provide a matrix below this 3 graph to help the user know what's the current impact of the wildfire. Yeah, this is the initial website only containing the past wildfire dataset. And also we also create a new web portal that help user to track the current wildfire. And this is the on the left part is contains like a map provided by the Google API, and also on the right part is some graph. It's some line chart or bar chart we generated. So for the left part, when we load this page, the website will directly call the current wildfire data through the Aries weather API, and then rendered this wildfire based on the location and also the wildfire size. So by the Google API. So yeah, this is the map, and when we drag it, like we can click on this circle, and the size of this circle represents the wildfire size. So when we click on it, it will show all the fire information, including the fire location, the fire size, and the fire starting time, and also the predicting control time. Yeah, so when we click on like the predict air quality, so we will automatically predict the data, predict the CO change, ozone change, and PM 2.5 change on the right part.
Okay, so for the red part, so the idea of our prediction is that
David, go ahead.
Yeah. So as we can see, we are predicting for the next 5 days. So according to Professor, so if we want to make this web page useful, we want to show the user the damage or the impact of the fire during the next 5 days. So the reason we do that, so the central idea of doing this is because for each of the day, the impact can be different based on our AI powered model. So as we can see on our right hand side, after he clicks the predict air quality for this currently active fire, our AI based model is predicting on the first day is 0. Around, so it is around 0.58 or something, and then the second one is trending, the third one is trending even higher. So as we know, different parameters behave differently. So first one is CO, the second one is PM 2.5, and the last one is ozone. And then lastly, we have this red bottom part This one is also driven by the API. So this one is just providing the user with the useful information regarding not only with the fire, but also with the current weather condition, so that they can decide whether it is okay to go outside. So for example, as we know, this one is highlighted in red, which means the UV index is pretty high. It can be a little bit dangerous to the human body. And then on the bottom part, we are also listing the temperature, humidity, and the next 5 days, similar to the air quality matrix, so that this portal is more user friendly, can provide more information. And then all of the other fire, as he showed, they are all containing different information regarding the current fire. And then those maps and then those highlighted red, they are interactively and simultaneously changed with the API. So user will see the latest fire info no matter when they load the page. Finally, this is our About Us page, and then this is our team member. Yeah, I think this concludes with our presentation. Thank you.
Okay, let me stop recording.